We've talked about resting membrane potentials, we've talked about EPSPs, IPSPs, we've talked about threshold. Let's put it all together and see how action potentials come about. So notice we have graded potentials, EPSPs and IPSPs are all going to converge in the axon hillock. So we're going to have synapses on dendrites. In this case, in this illustration, we see a couple of synapses on the soma. Doesn't matter. They're all going to flow down the dendrites, flow down the soma, and they're all going to converge. They're all going to arrive at the axon hillock. So notice the top neuron there, the pinkish one, it's releasing neurotransmitters that are opening sodium channels, all right, creating EPSPs. So those are going to flow down and converge in the axon hillock. The blue neuron on the bottom is releasing neurotransmitters that are opening either chloride or potassium channels, creating IPSPs. Those are likewise going to flow down, and some they're going to arrive in the axon hillock. So axon hillock is where all the graded potentials are summed up. It's where they all get added up together, all right? And what we're going to do then is we're going to see, do we have enough EPSPs to push the membrane potential from its resting value of -70 all the way up to threshold of -55. That doesn't necessarily happen every time. So we could have, for example, a whole bunch of IPSPs. They might greatly outnumber the EPSPs. In that case, we might go from the resting membrane potential of -70 down to -75, -80, -85. We're not going to have an action potential in that case. But it could be that we have more EPSPs than IPSPs, or we have bigger EPSPs than IPSPs. As a result, if we push the resting membrane potential from -70 all the way up to -55, that's the threshold value, then boom, we fire the action potential. And we talk about firing the action potential. That's why we call the axon hillock the trigger zone. It's where we pull the trigger to fire the action potential, okay? So that's what's going on with all these graded potentials. We're just looking to see, do we have enough more EPSPs that we're going to make it to threshold and have an action potential, okay? And notice this can happen in various ways. So on the left panel, we see what I was talking about initially. Maybe we don't have enough. Maybe the EPSPs and the IPSPs all cancel each other out, in which case we don't make it to threshold. See, on the far left panel there? We don't get there. Nothing happens. We grab a beer and watch TV. Nothing happens, okay? Or look at the middle panel. It could be that two graded potentials from different neurons add together. So graded potential from one neuron, graded potential from another one, in this case both EPSPs, they arrive at the axon hillock at the same time, and they add together to push the membrane potential over threshold. Then we have an action potential. That's called spatial summation because it's two different neurons that are adding together. Or in the right panel, we see where it's just one neuron. And what it does is it has a couple of big EPSPs in a row so that the two EPSPs add up together with each other from the same neuron, and in this case still push it over threshold. This is called temporal summation because it means instead of having two graded potentials at different points in space, we had them at different points in time. But they were still close enough together in time that basically the second one caught up with the first, so to speak, and the two of them together were enough to push us over threshold. Okay? So again, we're adding up graded potentials to see if we make it to threshold. If we do, we pull the trigger and fire the action potential. So, if we open a sodium channel on a dendrite, that's going to cause a what, resulting in a what? So if we open a sodium channel, is that going to make a depolarization or a hyperpolarization? And in turn, is that going to cause an action potential or a graded potential? Are you with me? Are you following? Yeah, sodium causes a depolarization. It's going to make the membrane more positive. And that's going to create a graded potential, which will flow down the dendrite or the soma, arrive in the axon hillock. It will then get added up with all the other graded potentials, and maybe they'll make it to threshold, maybe they won't. Okay? So here we see graded potentials will all arrive at and get summed up to create, if they push it over a threshold, then we create the action potential. So just to summarize, we've mentioned this a few times. Graded potentials were different sizes. Remember why? What causes graded potentials to be different sizes? Different strength of stimulus, all right? The light little tap or the hard slap, okay? So graded potentials can be big or small. Every action potential is exactly the same, all right? So what happens, once you fire an action potential, it's always going to be the same. You don't have big action potentials and small, all right? So when an action potential arises, it does what we call propagate down the axon. So it basically self-propels itself. Remember back at the beginning of the semester we talked about negative and positive feedback loops? This is the only positive feedback loop we're going to see in Bio 201. We're going to see how that works coming up. But the action potential is a positive feedback loop. It's like lighting the fuse on a stick of dynamite. Once you light the fuse, it's guaranteed to burn all the way down to the stick of dynamite and cause it to explode. All right? The action potential propagates itself. It's a positive feedback loop. Once you start it, it's guaranteed to go all the way to the end. Okay? When it reaches the axon terminals, it may synapse with another neuron and cause graded potentials in that neuron. So see, this is the great chain of events here. So starting from the left, neuron 1. So it has a synapse, releases some neurotransmitters, all right? Graded potentials flow down, all right? The dendrites and the soma, they arise in the, they get summed up in the axon hillock. They cause an action potential, which you can see those blue arrows, the electrical signal. Well, when that action potential gets to its own axon terminals, it will cause a release of its own neurotransmitters. And then they're going to flow down the dendrites. And they're going to arrive in the axon hillock. And maybe they'll make it to threshold, maybe they won't. Think about this. Every neuron, you have some latest estimate, I think it's like 86 billion neurons in your brain. Every one of them synapses on average with 1,000 other neurons. So you've got all these neurons talking to each other all the time. And that's what's going on. It's just always happening. Always having graded potentials, always having action potentials. It's just this massive flow of electrical signals all through your brain. And that's everything you do. That's thinking, that's memory, that's love, all right? So that's all of it. So now we're ready to look at the details of the action potential, which we're going to look at an overview here, and then we're going to dive in the next PowerPoint. So let's look at the overview. Action potential is a series of rapidly occurring events that change and then restore the membrane potential of a cell to its resting state. So during the action potential, we have voltage-gated channels. All right, so here's a big difference. The graded potentials were caused by ligand-gated channels. A couple big differences. So remember, the graded potentials were mostly on dendrites and soma. They were caused by ligand-gated channels. The action potential is on the axon, and it's caused by voltage-gated channels. And it takes just two kinds of voltage-gated channels to make the action potential: sodium and potassium. And what happens is, it's the graded potentials reaching threshold that cause these voltage-gated channels to open. Remember, voltage-gated channel means it opens because of electricity. Well, it's the electricity of reaching the threshold, all right? So we change from negative 70, the resting membrane potential, we change up to negative 55. When we hit negative 55, that is the magic voltage. That is the magic voltage that opens the voltage-gated sodium and potassium channels. And that's what's going to cause the action potential. Now, voltage-gated potassium channels take longer to open than voltage-gated sodium channels. So think about what that means. It means the voltage-gated sodium channels are going to open first. So what's going to happen when voltage-gated sodium channels open? Remember, that causes depolarization of the membrane. All right, so the sodium is going to rush in, depolarizing the membrane. And then, after the membrane gets depolarized by all the sodium coming in, right about that time, just as the sodium channels close, the potassium channels will open. And then all of the potassium will rush out. Now remember, potassium is positive, so what happens when a bunch of positive potassium leaves the inside of the membrane? That's going to hyperpolarize the membrane. So the sodium caused a massive depolarization, and then right about the time the sodium channels close, potassium channels open. That's going to now hyperpolarize. And so what that's going to do, it's going to bring us back to where we started from. So look at that graph on the left, all right? See, it says the depolarizing phase. Actually, look in the lower left-hand corner of that graph. See how we jumped from negative 70 to negative 55? That's what the graded potentials did. Once we hit negative 55, that opened the sodium channels, and then we have the depolarizing phase. Notice that the membrane goes all the way up to like positive 30. We let so many sodiums in that they cause the membrane to go all the way up to positive 30. And then, right at the peak of the graph, that's when the voltage-gated sodium channels are closing, and right about the same time, the voltage-gated potassium channels open. And when those potassium channels open, all that potassium flows out, and we have the repolarizing phase. So we go back down to where we started from. Now, in fact, we let so much potassium out that we go to negative. See how we dip down below negative 70? We go down all the way to, let's say, negative 80. That's called the after hyperpolarizing phase, okay? And that's going to play an important part coming up. That causes a certain phenomenon that we're going to name and talk about, okay? So, again, the sodium channel opens first. That causes depolarization. Then potassium channels open second. That causes repolarization. And again, we go a little too negative. So what actually happens because we go too negative? We create something called a refractory period. Actually, there are two kinds of refractory periods, and they're caused by two different things. There's, first of all, the absolute refractory period. During the absolute refractory period, it is impossible to have another action potential. And that's actually caused by the way the voltage-gated sodium channel works. So that's going to happen first. During that absolute refractory period, we absolutely cannot have a second action potential, and that's caused by some peculiar characteristics of the sodium channel. Then, even when the sodium channel resets and is ready to open again, the fact that we went too negative, the fact that we have that after hyperpolarizing phase, that means now that in order to get the threshold, instead of just going from negative 70 to negative 55, we got to go from like negative 80 to negative 55. We have to go farther. So that means it's going to take a bigger stimulus to get us there. That's called the relative refractory period. So two kinds of refractory periods. One caused by the peculiar way the sodium channel works. The second caused by the fact that we let so much potassium out that the membrane became too negative. Okay? Let's take a look. This graph on the left, I can promise you this will show up on either a quiz or an exam. So here you go. I'm telling you right off the bat, make sure you know this. If you do, you'll get all the points you need. So let's take a look, all right? Let's take a look at the little numbers there and figure out what's happening at each number. So at number 1, this is where the graded potentials are summing up on the dendrites and on the soma. So see how it's going at negative 70. We were at the resting membrane potential. Now if we get enough EPSPs to push us all the way up to threshold, that's what's happening at number 1. So at number 1, we're apparently getting a lot more EPSPs, or we're getting bigger EPSPs than the IPSPs. So we are pushing the membrane all the way up to threshold, and that's what happens at number 2. At number 2, we hit threshold. And what's the magic of threshold? Why is it so special? Threshold is the electrical value at which the voltage-gated sodium-potassium channels open. Remember, a voltage-gated channel only opens at a certain voltage. Well, what voltage do these ones open at? Negative 55. Negative 55 actually opens both of those channels. But again, here's the deal. The sodium channels open immediately, whereas the potassium channels take a while before they open. So what's going to happen then? Look at number 3. the sodium channels are opening first. So all that sodium is coming in. Remember, the sodium-potassium pump had previously pumped all the sodium outside. We had a huge concentration gradient. So the moment we open that voltage-gated sodium channel, whoosh, sodium just comes rushing inside the cell. And it changes it from negative 55 all the way up to like positive 35. That value, positive 35, by the way, some books have positive 30, some positive 35, some positive 40. You don't have to know that number exactly. Negative 70, negative 55, you have to know those exactly. The other one, just say positive 30 to positive 40. I'm good with that. So, sodium channels open first, so we get a depolarization. That's what's happening at 3. All right, the membrane is depolarizing all the way up to positive 30 to positive 40. Then, what's happening at 4? At 4, this is where the sodium channels shut. Remember, they opened first. They are now shutting just right about at the same time that those potassium channels are open. Those voltage-gated potassium channels are finally opening. So what's happening now? Well, remember, the sodium-potassium pump had previously pumped all the potassium inside the axonal membrane. So now, once we open that voltage-gated potassium channel, all that potassium is going to go flowing out. It's going to leave the inside and go out into the extracellular fluid. And since it's positive, we have whole bunches of positives leaving the inside of the membrane. And if bunches of positive leaves, that means we become more negative. So that's called repolarization. Look, we're becoming more negative. We're going from positive 35 all the way back down. We're dipping below negative 55. And look, oh my God, we dip all the way below negative 70. Down to negative 75, negative 80, negative 90. I don't know, just depending. It can be any of those. You don't have to know that number exactly. So at 5, that's what's happening. Potassium is rushing out, repolarizing the membrane. At 6, so much potassium leaves that we hyperpolarize the membrane. We're more negative than the normal resting membrane potential. We're not at just negative 70 now. We're at negative 75, negative 80, negative 90. We're too negative. But then look, eventually the membrane potential comes back to normal. It comes back to the resting membrane potential again of negative 70. How could that happen? Remember, as a result of the action potential, everything is now back asswards. All the sodium, which is supposed to be outside the cell, has now come inside. And all the potassium, which is supposed to be inside, has now gone outside. So the whole world is inside out, upside down, back asswards. Oh my God, how will anything ever get back to normal again? And we know the answer to this. It's what burns 40% of all your ATP at rest. It's the thing that's working 24/7, 365. Yeah, those sodium-potassium pumps are so efficient that within just a fraction of a second, they will pump all that sodium back out, and they will pump all that potassium back in, and the whole world will be right again, okay? So there you go. That is the action potential. That's the preview of it. That's the way it's going to work. And in the next annotated PowerPoint, we're going to take a look at the actual details of the action potential.